3-2 polynomial functions of higher degree. We're going to be looking at transformations. We're going to sketch these polynomial functions, figure out what the heck a polynomial function is. That might be a good idea. Leading coefficient test. You remember what a leading coefficient is? First one, number in front of the x. I mean, y'all are on to something, but I haven't heard the correct answer yet. We're going to find real zeros of polynomial functions and talk about the intermediate value theorem. So it is. It is. So is that how they leveled it? Okay. Okay, so some of the features of a polynomial function. A polynomial function is continuous, meaning I can draw the entire graph without picking my pencil up. It's continuous. There's no holes in it. There's no breaks. It's one continuous smooth curve. Okay, so this is a polynomial function. There you go. If you were graphing it, yeah. Okay. This graph here is obviously not a polynomial function because there's got a break in it, right? So this is a piecewise function. Now, is it possible to draw a piecewise function with no breaks in it? Yes. Does that make it a polynomial function? No. Okay. So because there's some other rules we have to apply as well. This, so it's continuous, and I've already said some of this already. A second feature is it's only smooth, rounded turns. Does all that look smooth and rounded? Okay, so far this is a polynomial function. This is probably a polynomial function of at least 5th degree. I can tell that just by looking at it. It's at least a 5th degree polynomial. What does that even mean? We'll talk about it later. Yeah, we'll get there. Is this a polynomial function? Why not? That's not round and smooth, is it? The absolute value function, is it continuous? Yes, absolute value is continuous, but it's not rounded, it's not smooth. Okay, so this is not a polynomial function. Using the features presented in this section, along with your deep, vast knowledge of plotting points, you have a deep, vast knowledge of something. Anyway, plotting points. What are intercepts? X-axis or Y-axis, right? We have both types of intercepts. We know about symmetry. So we're going to accurately sketch by hand a polynomial function. Polynomial functions that has the simplest graphs are monomials. Monomial means one term. Okay, so if I have a graph f of x equals x to the nth power, that is a monomial. So we're going to take a look at a couple monomial functions. Obviously, n has to be greater than 0. So here are two polynomial functions. The one on the left, you see there's two graphs there. The one that's graphed lightly is y equals x squared, which is the parent quadratic, right? The dark one there, that's y equals x to the 4th power. How are they different? Exponents are different, not as rounded, not as rounded. Okay. Anything else that's similar about x squared and x to the 4th? They share 3 points. What are you gonna say? We've talked about one being wider. Which one's wider? Bigger exponent. Okay. Which one goes up faster? Well, the bigger exponent. Kind of interesting there. Okay. So those both have even exponents. Okay. Any other similarities you see in those two graphs? which is the same point. They both intersect at the point 0, 0. Okay. Anything else that's similar? They both have a parabolic appearance. Yeah, but we don't call x to the fourth a parabola. Okay, but I agree. They're okay. They're both going up on both sides. That's kind of interesting. The other one, I have a graph of x cubed and x to the fifth. Similarities, differences. How are they similar? X to the third, it's the light one here, and x to the fifth, it's the dark one. We were comparing the light one and the dark one. Now we're comparing this light and dark one. Okay, so we're now on graph B for those of you that have not been with us. Now that everybody's together, what similarities do you see here between these two graphs? They share a few points. What else? Same shape. Do what? Exponents are odd. They're going the same direction. On the left side, it's going which way? To the left, it's going. To the right, it's going. Very important. Second period didn't notice that. Okay. What else is going on? Okay. But it's not constant. Okay. It's not constant. X to the third and x to the fifth are both always increasing. There is some slight slant to both of them. However, one appears to stay closer to the x-axis for a longer period of time. Fair enough? Domains and ranges are all real numbers. Okay. All right. Good. Good, good, good. The bigger the value of n, the flatter the graph at the origin is what it will look like, but it's never going to be flat. Okay. So x to the 22nd. X to the 22nd would actually go back up here. X to the 22nd would look a lot like x to the fourth, but it's going to be going up faster, though flatter longer, or appearance of flatter longer. Okay. Okay. Based on that information, let's sketch f of x equals negative x to the fifth power based on what you know. No calculators. Let's just think about what this guy looks like. Nice. Type here. Type here. Type here. Just type wherever you want to. I don't want to type anywhere. Now I got these random dots. Whoa. Okay. What's it look like? That's an XY axis. Okay. So we've got a reflection across the x-axis. Okay. What else?
It's an A in a circle. It just kind of looks
I'm trying to find some decent answers and I'm failing. Okay. So it's reflected across the x-axis. Okay, relatively flat near the origin. So it's down over here. Okay, so it's coming down. It's going to be very steep, right? So it's very steep. It appears to flatten out, and I missed the origin altogether, but you get the idea. Okay, so that is a very, very rough sketch of what it looks like, right? I'm going to move the box in a minute, and you can see the good drawing. What? Because we've paid attention during class when we talked about graphs and transformations. and a negative sign does a reflection across the x-axis. Correct. We just talked about that on the last slide. Okay. Part B. What's it look like? Move to the left one. Has a parabolic appearance. Okay. It's going to look flatter near the origin. Going up. Yes. Okay. Fourth power makes it stay. We talked about that already. I'm serious.
Axis of symmetry is -1.
Axis of symmetry is x equals -1. Okay. All right. Here's part A. There's the graph. It appears to be flat near the origin. It is a reflected x cubed graph because of the negative sign. Great job. Y'all described it well. Part B, just like you said, move it one to the left. It's still opening up, has a parabolic fill, appears to be flatter near the x-axis. Okay. Y'all are doing well. Moving on. So in example 1, both graphs will eventually rise or fall without bound. Did y'all notice that? Both graphs are either rising or falling without bound. Okay. When we're talking about a graph rising or falling, we're actually talking about going to the left and going to the right. But when we're talking about domain, we're going from left to right always, correct? So what we're talking about here, when we're saying it's going to eventually rise or eventually fall, we're talking about something that's called end behavior. What are the ends of the graphs doing, if you will? Okay, what are they doing? To determine whether it's going to rise or fall, we have to look at the function's degree to determine if it's even or it's odd, and look at the leading coefficient, whether it's positive or negative, and obviously the leading coefficient. I'm going to go back to the graphs real quick. This was the graph of x to the 5th. This is an odd function, isn't it? Odd. Okay. Well, let's reverse that. The degree is odd. I'm not going to call it an odd function. The degree of the function is odd. Okay. Because the degree of the function is odd, what are the ends doing? What are the ends of this one doing? They're separating. They're going their own way. Okay. The single man out. Okay. When the function is even, what are the ends doing? In this case, they're both going up. Evens. We're talking about pairs. Okay. Pairs tend to go together. That makes sense? So if it's even, you're working in pairs. They're either both going up or they're both going down. When we're talking about odd, we're talking about individuality. They're doing their own thing. One's going down, one's going up, or one's going up, one's going down. Okay? That's end behavior. The leading coefficient test, as x moves without bound to the left or to the right, the graph of the polynomial function eventually rises or falls in the following manner. This is a very generic way of writing what a polynomial function looks like. All polynomial functions look like this. Okay, the a sub n, whatever, all the way to a sub 1, a sub 0, those are simply your coefficients. And the subscripts indicate that they're not necessarily the same. Then up at the top, you have x to the n, x to the n minus 1, x to the n minus 2, blah, 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 x to the first, x to the 0. Okay, descending powers, correct? Okay. So when n is odd, when the degree of a function is odd, if a is positive, it's going to be down on the left, up on the right. For instance, y equals x cubed. Y equals x cubed is odd. The leading coefficient is 1. It's down on the left, up on the right, isn't it? However, if the leading coefficient of an odd degree function is negative, it's flipped. And y'all have already seen that today. You've talked through it. Okay. I'm going to tell you right now that the first graph is at least a third degree function. This is at least x to the third. Could be higher, but it's at least a third. I'm also going to tell you that this one is at least a fifth degree function. Could be higher, but it can't be lower. This is at least fifth degree. I can tell that just by looking at it. Okay. Do y'all see any connections where I got those numbers? What are you thinking? This is only turns twice. I said this is at least third degree. Okay. You're onto something. You're onto something. Okay. We'll talk about it more in a little bit. So odds, and then a lot of times like this one right here, I might call this one a, athletes love these. Actually, let's do this one. This one is a up down. Y'all like up downs, right? Okay. So that's kind of a lazy way of me talking about it. When I say up down, I'm saying it's up on the left, down on the right. Okay. And this one would be a down up. Now, why do they call them up downs? Because don't you start up downs in the down position and up position? So if you're in the up position doing up downs, don't you go down first? You start from up. Okay.
Oh, that makes sense. That doesn't make sense.
And if you took, this is quite interesting too. What? So this says what? And now it says down. Okay. So odd, they go their separate directions. Even, the one on the left, they're both going up. That's because the degree is even. The leading coefficient is positive. That one right there is at least a fourth degree function. Okay. The one on the right, it's at least a second degree function. It is even. Leading coefficient is negative. Makes it go down. So I might call this one an up, up. And this one I would call a down, down. Okay. I just want y'all to understand when I'm saying these, that's what I'm talking about. I'm talking about what's the left side doing, what's the right side doing, in that order. Okay. That's down. Letter A, it says describe the right hand and left hand behavior of the graph of each function. All right. Letter A. Listen to my questions. Letter A, what is the degree? Third degree. What is the leading coefficient? -1. What is the leading term? -x cubed. The first term is -x cubed. That's why the leading coefficient is -1. That's why the degree is 3. Okay. What is the left-hand side going to be doing? As this graph moves to the left, what's it doing? Okay. On the left side, it's up. And on the right side, it's down. Okay. I don't know what it's doing between those ends. I don't really care. The question just asks, what's the end behavior? So I would call this one an up, down. Okay. It's up on the left, down on the right. Part B, degree. 4, leading term. Leading term. Leading term. X to the 4th. Leading coefficient. 1. Keep saying 1, we'll eventually get it right. Okay. In general, what are the ends doing? Staying together, right? Because it's even. Because it's even, they're staying together. Because A is positive, they're going up, up. Okay. C, leading term, x to the fifth. Degree, fifth. Leading coefficient, 1. The function is even or odd? Function is odd, meaning the ends do opposite things. In this case, doesn't matter. This is a down up. It's x to the fifth. X to the fifth. Okay. Do I care about the x? I do for graphing. Do I care about the x for discussing end behavior? No. Which piece of that graph is the most powerful? X to the fifth is the most powerful. Okay. So it controls the end behavior. The highest degree controls the end behavior. Okay. Moving right along. Here is their explanation of part A. They actually have a graph of it. By hand? Oh, we'll talk about it. Go ahead. That actually takes longer. It takes more time than just look at it and say it's an up down. Well, sure. Okay, here's the explanation for the second one. We said it was an up up, and there it is. And the third one, we said it was down on the left and up on the right, and there it is. Okay. The leading coefficient tells you only whether the graph eventually rises or falls. That's all it tells you. Okay. Other characteristics of the graph, such as where's the x-intercepts? Where are the y-intercepts? What are the minimums? What's the maximums? Do we have any relative minimums? Do we have any relative maximums? All that stuff we have to figure out using other methods. So the leading coefficient test only tells us what the graph is doing, if you will, as it goes to the left and goes to the right. Okay. It can be shown for a polynomial function of degree n, the following statements are true. Number 1, function f has at most n real zero. Okay, n is our exponent. Okay, I want to point that out. N is the exponent. If I have a 5th degree polynomial, what is the maximum number of real zeros a 5th degree polynomial can have? 5. Okay, let me change gears. How many solutions does a 5th degree polynomial have?
4.
It will have 5. A 5th degree polynomial does have, I guarantee it has 5 solutions. What is number 1 saying? It says at most real zeros. So a 5th degree polynomial could have 3 real solutions and the other 2 are imaginary. Or maybe it has 1 real solution and the other 4 are imaginary. Okay. We are using imaginaries now. Okay. Number 2. Caddy was kind of on this. She was saying the wrong thing. The graph has at most n minus 1 turning points. So if I have a 5th degree polynomial, at most it turns how many times? 4 times. So a fifth degree, so a x to the fifth plus other stuff. That graph could look like, well, we've seen one. How many turning points does that guy have? 0. A turning point is when it changes from increasing to decreasing or decreasing to increasing. This guy here is always increasing. Okay. A fifth degree polynomial could look like this. How many turning points does that one have? 2. Is that less than 5 minus 1? A fifth degree polynomial could look like this. How many turning points does that have? 4. Okay. That's why it says at most. So turning points are also called relative minima, relative maxima. And again, that's where it changes from increasing to decreasing or vice versa. Finding the zeros of polynomial functions is one of the most important problems in algebra. We do that all the time, finding the zeros. Questions on this so far? Okay. I have told you, and you've heard it from other teachers in the past, that zeros, roots, solutions, and factors are all the same. You've heard that, right? Okay. It's pretty much true. It's kind of stretching it a little bit. So a little bit more detail about what those mean. If x equals a, that means that a is a zero of the function. That's what that means. We can also say if x equals a, then a is a solution to the polynomial, meaning if we take that value a, plug it into the polynomial, we're going to get 0, right? So those are very much the same. Here's where the change comes. We've said in the past that a is a factor, and that's false. Really, x minus a is a factor. Okay? So whatever a is, now let's think about that. If you took x minus a and set it equal to 0, you would have x minus a equals 0, which leads to x equals a. Okay? But the factor that the a came from is x minus a. We've talked about this being the same thing as an intercept. No, an intercept is a point. It just so happens the x-intercept has the coordinate a, 0. So there's a little slight difference in what they mean, but it all comes from the same point. Okay? Find all the zeros to the function 2x to the fourth plus 2x squared, negative 2x to the fourth. If I want to find the zeros of a function, first thing I want to do is factor it. I mean, that's how you find them. Once you factor, you can find the zeros, right? Because you set each factor equal to 0, solve for x, and that's the 0. So for this particular problem, what would y'all do to try, after we've set it equal to 0, what would y'all do next to try to find the zeros? Do what? Okay. Yes. But because the leading term is negative and factoring out, instead of factoring out 2x squared, we're going to factor out a negative 2x squared. Okay. So if I was to factor a negative 2x squared out of that, what's left? Okay. Am I done factoring? What can I factor? Do what? X minus 1 squared. Okay. What does x squared minus 1 factor into? There you go. Okay. Real quick, at most, how many real solutions does this guy have? At most, this has how many real solutions? 4, because of the degree, right? Okay, keep that in mind. This thing has at most 4 solutions. How do I find the zeros now that I factored it? Set each factor equal to 0. I'm going to work backwards. I'm going to work from right to left. So x minus 1 equals 0. X minus 1 equals 0, which means x equals. That's one of my real solutions. Next one. X plus 1 equals 0, which means x equals -1. Okay, I'm going to be picky for just a second. I'm not going to spend a lot of time on it. Can't you factor x squared? X squared is what? X times x. That makes sense? We're not going to right now, but let's set this last factor to 0. -2x squared equals 0. Divide both sides by 2, -2. Take the square root of both sides. X equals 0. Okay, that's 3. But really, this is an x and an x, which means the other 0 is 0. There's the fourth one. So the 4 zeros of this function are -1, 0 with a multiplicity of 2. We'll talk more about that later. And 1. That adds up to 4, right? -1, 0 with a multiplicity of 2, and +1. Okay, that's 4. Okay. I don't know. What? Okay. There it is. There they are. There's talking about the repeated zeros we just did. Standard form, descending degree. I don't know why. Sometimes they call it standard form and sometimes they call it general form. Okay. Descending powers. We'll talk about the intermediate theorem tomorrow. And we're going to have to move tomorrow.